So in this video, we're going to be talking about lines in space. So in 2 dimensions, you will remember that a point and a slope would define a line. And it comes with the equations y minus y1 equals m times x minus x1, and y equals mx plus b. In 3 dimensions, we need a point and a vector to determine a line. So let's visualize this in a 3D space. So let's say we have this blue line in the 3D space. We can call this line L. Alright, so how can we write a vector equation of this line? First, we have a vector that goes along the line. We can call this vector v. And then we need a scalar in front of this vector. We can call the scalar t. This just allows the vector to go forward and backward at any point along this infinite line. When dealing with vectors, we usually start from the origin and we go out. To get from the origin to any point in the line, we have vector r0 or r0, and then we can call the resultant vector, which is the sum of r0 and tv, vector r. So the vector equation of a line in 3D space is just r of t equals r0, which is the vector that gets us from the origin to a point on the line, plus t times vector v. Vector v is the vector that goes along the line, and t scales it so that it can go forward and back as much as you want. So all these vectors, r0, r, and v, they describe 3 dimensions. So we have an x, y, and z coordinates. We can parameterize the equations into each of the respective coordinates. So let's say vector r0 takes us from the origin to a point on the line. That point, we can name it p0, and the coordinates at point p0 is x0, y0, z0. So again, we can have vector v go along the line L, and let's say that the components for vector v is vx, vy, and vz. The parametric equations for the line can be written as x equals x0 plus t times vx, y equals y0 plus t times vy, and z equals z0 plus t times vz. So these parametric equations allow us to break up the equation of the line into the 3 variables. There's also another form called a symmetric equation. And all this is that from the parametric equation, we just isolate for the variable t. So the symmetric equation is x minus x0 over vx equals y minus y0 over vy equals z minus z0 over vz is equals t. Okay, so let's do some examples. Number 1, write the equation of a line through 2, 3, 2 in the direction v equals -1, 5, and 3. So remember, our vector equation is r of t equals r0 plus t times v. And then r0, that is the vector from the origin 0, 0, 0 to a point on the line. So we are given a point on the line 2, 3, 2. We can call this p0. So our vector for r0 equals 2, 3, 2. So our equation can be written as r of t equals 2, 3, 2 plus t times, and then v is given as -1, 5, and 3. That is our vector equation. We can also write this in the parametric form. Now we're just breaking it down by each component. So starting with x, we have x equals 2 minus t. The 2 comes from the r0 here, and we want the x component from the vector v. And then we're going to do the same thing with the other components. Y equals 3 plus 5t. And we have z equals 2 plus 3t. And then we can also write it in symmetric form. We're isolating each equation to solve for t. X minus 2 divided by negative 1 equals y minus 3 divided by 5 equals z minus 2 divided by 3 equals t. Alright, example 2. Write the equation of a line through the points 1, 3, 5 and negative 2, 5, 9. So let me write out the vector equation again. Alright, so for the equation, again, we need a point and a vector. So in terms of the point, we can choose any of the 2 points. I'm just going to choose 1, 3, 5. And that's just going to be the vector for r0. So 1, 3, 5 is the vector that takes us from the origin 0, 0, 0 to the point on the line 1, 3, 5. Now we need to find the vector v. Since 1, 3, 5 and negative 2, 5, 9 are both points on the line, we can find the vector along the line by subtracting one point from the other. Let's say we choose negative 2, 5, 9 to be our final point and 1, 3, 5 to be our initial point. If we do final minus initial, we'll get that our vector v equals negative 2 minus a 1, so that's negative 3. And then 5 minus 3, so that's 2. And a 9 minus 5, that's a 4. And then it doesn't matter what points we choose as our final or initial, because the scalar t accounts for spanning across the infinite line. And then for the parametric equations, we separate the equation for the different components. X equals 1 minus 3t. Y equals 3 plus 2t. And z equals 5 plus 4t. And then again, for symmetric, we isolate for t. T equals x minus 1 divided by negative 3 equals y minus 3 divided by 2 equals z minus 5 divided by 4. Alright, so example 3, write the equation of a line through the point 1, 1, 2 and perpendicular to vectors 2, 2, 2 and 1, negative 1, 1. So for the vector equation, we need a point and a vector. The point is already given as 1, 1, 2, and the vector is perpendicular to two other vectors. So I'm already immediately thinking cross product. So we need to take the cross product of 2, 2, 2 and 1, negative 1, 1 to find the perpendicular vector to both of those. So from the previous video, we can use a 3x3 determinant to find the cross product of those two vectors. So again, multiplying the diagonals, we have 2 minus a negative 2, and then a negative 2 minus 2, and then 2, negative 2 minus 2. So the perpendicular vector is 4, 0, negative 4. So now that we have a point and a vector, we can put it in the vector equation. R of t equals 1, 1, 2 plus t 4, 0, negative 4. Now let's talk about the distance from a point to a line. When we are talking about calculating the distance between a point and a line, we are talking about the shortest distance between them. So if we draw the shortest distance with a line from point Q to L, this line should be perpendicular to L, and we can call this line D. That is going to be the shortest distance between Q and L. So let's say we're given a point that is on the line. We'll call this point P. If you draw a line between P and Q, you notice that this is not necessarily the shortest distance. But in doing so, we did create a right triangle. So we can use known values to get the relationship to find the distance. So let's call theta this angle. So in relation to theta of the right triangle, D is the opposite side and line PQ is the hypotenuse. Since sine is the opposite of our hypotenuse, we can write a sine equation. So we have sine of theta equals the opposite, which is D, over the hypotenuse. The hypotenuse is the length of line PQ, so since we're only concerned about the length here, we can say this is the magnitude of vector PQ. Solving in terms of D would give us D equals the magnitude of vector PQ times sine theta. However, we usually do not know what the angle between line PQ and the blue line is, so we can't have theta in this equation. But we can make a substitution if we can find some sort of way to get this in the form of another equation. So this portion right here, the magnitude of PQ times the sine of theta, that is almost like the magnitude of the cross product equation. So the magnitude of A cross B equals the magnitude of A times the magnitude of B times sine of theta. And again, theta is the angle between vectors A and B, where both vectors A and B share a point on their tail. So if we look back at our distance equation, we're missing a magnitude of a second vector. Now, recall that we have a vector v that goes along the line. We can make vector v go from point P along L. So now we have our second vector, and the angle is between vector v and vector PQ. So we can multiply the magnitude of vector v on both sides of the equation. So now we notice that this is in the format of the magnitude of the cross product equation. We have the product of the magnitude of two vectors times the sine of theta. So we can rewrite the magnitude of PQ times the magnitude of V times the sine of theta into the magnitude of the cross product of PQ and vector V. Now if we want to isolate for the distance D, we have D equals the magnitude of PQ cross V over the magnitude of V. And this is the equation of the distance from a point to a line. So now let's do an example. Find the distance between point Q223 and the line L, given by the parametric equation. X equals 1 minus t, y equals negative 3t, and z equals 2 plus 2t. So let's write this line in vector equation. We have r of t equals 1, 0, 2 plus t times negative 1, negative 3, 2. Remember, this is the vector that takes us from the point 0, 0, 0, which is the origin, to 1, 0, 2, which is a point on the line. And then this part, this is the vector v along the line. So we can draw a picture. So this is point Q, and we want to know how far it is from the line L. And again, the distance to it, if we make a line, is perpendicular to line L. And then the point on line L, 102, let's call that point P. And then we have our vector V. So remember, the formula to calculate the distance from the point to line is D equals the cross product of vector PQ and vector V, the magnitude of that, divided by the magnitude of V. So let's get vector PQ first. So vector PQ is the components of Q minus the components of P. For X component, we have 2 minus a 1, so which is a 1. And then we have a 2 minus a 0, which is a 2. And then we have a 3 minus a 2, which is a 1. Now let's take the cross product of P, Q, and V. So this is 4 minus a negative 3 for the X component, and then minus, and then a 2 minus a negative 1 for the Y component, and then a negative 3 minus a negative 2 for the Z component. So PQ cross V should give us 7, negative 3, negative 1. So going back to the equation up here, the magnitude of PQ cross V is the square root of the sum of the components squared. So square root of 7 squared plus negative 3 squared plus negative 1 squared. This is divided by the magnitude of V, which is the square root of negative 1 squared plus negative 3 squared plus 2 squared. So this should equal the square root of 59 divided by the square root of 14. Which means that the distance between point Q and line L is approximately 2.053 units.